Am I audible? Can you please confirm? Varun, can you hear me?
Yes, sir.
Okay, okay. So let us begin today's session. Welcome all of you for the first live session of this Power System Engineering NPTEL course, and I will be one of the TAs for this course. So, let me first introduce myself. I am Gagan Meena, and I am doing PhD at IIT Bombay in Power System Engineering. So, this will be the agenda for the live sessions. Means I have decided this, but you can also suggest me if you want some changes in this. So I will just briefly discuss the first of all, first discuss a brief overview of week 1 quickly, and then we will see questions. We will solve certain problems, and then we can have your doubts. And in between, also, if you have any doubt, you can ask. And just to remind you that this deadline for the first assignment is February 7th. So please submit the assignment on time. And you can also find these recordings for this live session on this link. This link will be available on the portal. On the right side, there will be a small problem solving session link. In that, you will find all the link for recordings as well as the PPTs which I am using. So all the three TAs will upload their respective PPTs as well as links in that Google Sheet. So let us just go through overview of week 1. So in week 1, mostly the overhead line insulators were discussed, and lastly a few introduction to cable was also given. And next week we will continue with the underground cables for distribution system. This was the overhead insulators. So can you tell why do we use insulators? Can anyone of you tell why do we need insulators? Anyone? So basically, we have these conductors, right? We want to transmit power from one distance to one point to another, and for that we have to carry these conductors over a tower. And the tower is also conducting. It is made up of metal, and conductors are also carrying current. So in between, if the tower has to hold the the conductors, then there should be some insulation so that there is no leakage, or there is only minimal leakage from conductor to the ground. We would have seen insulators in distribution system, also in towers, in railway traction whenever we go to railway station or metro station, and also in transmission system. When you go in remote places outside city, you will find very big towers. So these are high voltage, extra high voltage, or ultra high voltage transmission lines. They have these different types of insulators. So they separate the line conductors from each other and also from the tower. That is the supporting structure. And there are certain considerations which are required while designing these insulators. So they should have very high permittivity. So that means that their dielectric strength should be very high. And they should also be able to withstand over voltages because there are phenomena like surges or there are lightning phenomena. Lightning stroke is very common, and as a result of that, these insulators need to withstand those voltage. Although these lightning strikes are there, but they are of only very short duration. So for short duration, these insulators should be able to, even these lines also should be able to withstand that over voltages, that transient over voltage, or few milliseconds or seconds. For that also they have to withstand the over voltages. Then they should have very high mechanical stress because they have to carry, they have to bear the conductor load. The conductors are very heavy, especially when you go to very high voltages, extra or ultra high voltages, and sometimes even more than one conductors are there to reduce the reactance of the line. So there are these are called bundled conductors. So we can, because of reduced reactance of the line, more power can be transmitted over the same line. So there can be four conductors, six conductors bundle. I don't know whether you would have seen or not, but four conductor is very common. Six conductors also you can find, but very few. But four conductors is very common. And you would have also seen double circuit lines on same tower. There are three conductors on right side, three conductors on the left side. Or you can even have sometimes six on right and six on left. So, so the tower has to carry so much load, mechanical load. The insulator should have high mechanical strength to bear that load, even under worst loading conditions, such as during stormy weather, or in India, especially in Himalayas, where there is icing. So when the ice covers the conductors, then the load of the conductor, mechanical load increases, its weight increases. So that also insulator has to bear. So all these considerations need to be taken care while designing these insulators. And then it should have high resistance to the temperature change, so that there is no problem due to flashover. And also that I was also telling in the beginning that there should be, we don't want any kind of leakage. So leakage should be very minimal, leakage of current to the earth through via tower. Then the material also should be non-porous and impervious to atmospheric gases to reduce its corrosive effects, so degradation of the material. And it should also be free from any kind of impurities and cracks, which also reduces, because if impurities and cracks are there, then these dielectric strength as well as these flashover, the dielectric strength reduces, flashover increases, all these problems are there. Then the next part which was discussed was the electrical failure of insulators. So first one is, there are two types of failure. One is puncture and another is the flashover. So puncture is, what happens in puncture is that the arc, electrical arc, it passes through the body of the insulator, and after that, that insulator is, it's there is a permanent damage of the insulators, and we cannot use that insulator further. So the nature is, so how we can reduce this? The remedy is to provide sufficient thickness of the material so that we can prevent it. And then flashover is, it is arc between conductor and the earth, or the, we can say, through the tower. It happens because of the air surrounding the insulator, and it happens when there is wet surface during rainy season, or even during winters due to this mist or fog. Sometimes the surface become wet. At that time, this can happen, flashover. And this can also be reduced by increasing the resistance to leakage path. So we create these rain sheds. Then we discuss different types of insulators: pin, suspension, strain, tension, post type. This you have seen. These are just some pictures of different types of insulators. You can see strain insulator here. So strain insulator are used. Can you tell where strain insulators are used? These are the same suspension insulator which are used as
At the corner point.
yes. So corner point where the direction of line is being changed or at the dead end also. In both the cases, so it provides the mechanical stress for handling the mechanical stress. You can see here. So here there is a change in the direction of the line, and they can also be used in horizontal way. So here also, in whenever it is used as a strain insulator, it is always in the horizontal position. This one is vertical, so mostly you will see vertical. But during first as a strain insulator, and when the loading is too much, then these are also used in horizontal way. Here we can see in second picture, because the line loading is too much, you can also see that there are four. It's a bundle conductor. There are four conductors. You can see here. Can you see four conductors? Is it visible? You can see here. These are the four conductors. Here also you can see. There are four conductors. It's a bundle of conductors. So because there are four conductors, the mechanical load increases as a result. To keep the tension, these suspension insulators are used in the horizontal way. And if single insulator is not able to withhold that much mechanical loading, then parallel is used. That's why we can see here there are three parallel strings of insulator. And these are toughened glass insulators, and these are porcelain based insulators. Mostly you would have seen these whenever you go out. Then this is V string. This also it was discussed in lecture. So can you tell why V strings are used? Here also it's a bundle of two conductors. There are two conductors in one phase. So it's a bundle of two conductors. These are vertical V strings which are used so that there is to prevent any kind of conductor movement at towers, and it has several advantages. It will reduce the requirement of spacing between the conductors and between conductor and the tower because of the reduced movement. And because we have reduced that spacing, cross arm length also required, that is also reduces. So right of way requirement reduces, and if distance between conductor reduces, then the inductance also reduces and the power carrying capability increases. That's why it's very beneficial. So can you tell some advantages of using this suspension type of insulators? So in suspension type, we have these strings, multiple elements, multiple units in a single string. So what are the? Can you tell some advantages? So here you can see one, two, three, four, eight. Eight units are there. Roughly, if one unit is of 11 kV, so it's around 88 kV in eight units.
Basically, those type of systems designed for the high voltage purposes.
High voltage.
For high voltage
Sorry,
system,
I could not. Yes, yes. High voltage system.
and each disk is designed for the specifically 11 kV purposes.
Yes. So that is correct. It is for high voltage system, and one important one thing is that if one of the units somehow it gets damaged, we can replace it. We can replace that simply,
Yes,
and even if it is damaged, it can still provide the insulation, and the conductor can still carry the power because it is modular. So we can also increase. Suppose if the loading requirement increases and we want to increase the voltage level, we can add more insulators in that link, in that string, more units of insulator. So that is also easy to do in this case, but it's not possible in pin type insulators. So we'll move. So we'll start with question. I will solve problems. Initial 3 4 problems are uh, MCQ type. Then we will do numericals. So this is the first question. Which of the following statements is or are true or false? The first one is pin insulators are always used in tension. And second, that pin insulators are only used in voltages up to 33 kV. So what do you think?
I think option B.
Yes. Which one? Which statement is correct? So is this correct that pin insulators are always used in tension? The pin insulators are generally used at distribution level. Right? You can see in distribution system. Generally, these are in vertical position, but they can also be used in horizontal position for providing tension. So they are not always used in tension. Most of the time, they are used in vertical position, but whenever there is dead end or same as transmission system or there is change in direction, these are used for providing tension also. So it can be used for both, not always for tension. Then they are used for low voltages for distribution system. So this statement is correct and this first one is not correct. So this is true. Statement 1 is false and statement 2 is true. Then second question is the use of strain insulators can be observed. Yeah, this we have already discussed, but so can you tell what is the answer? Where are strain insulators used? A, B, C, or D?
So option A.
Why
I think
not?
option A.
Why not B?
mm,
So you had mentioned right that whenever we want to change the direction, then we require a strain insulator. So this anchor tower means that same. It provides a facility to change the direction of the transmission line. So this both are true. So this will help in changing the direction of the transmission line. So either A or B. So D is correct. Is this fine? Shall we move?
Yes, sir. Yes, sir.
Okay. So next is this also we discussed. Occurrence of puncture on an insulator can be lowered down by which option? Increasing the thickness of insulating material or increasing the resistance to leakage current or both or none. None of the above. So, can you tell?
I think sir, first one, sir.
Yes, correct. So increasing the thickness of the insulating material. This is for increasing the resistance will result in reducing. It will help in reducing the flashover. So this is a remedy. Second one is a remedy for the flashover, for reducing the flashover. So this is also a very simple question. So if puncture voltage and flashover voltages are given for an insulator, which is 125 kV RMS and 62.5 kV respectively. So what is the factor of safety? What can you determine this factor of safety using this information given in the question? How will you calculate factor of safety? So first question is, can we obtain the factor of safety using the information given in the question? Yes or no? Anyone? Yeah, we can actually we can determine.
Second, sir, factor of safety maybe two, sir.
Two, yes, correct. So we can determine, and it is a ratio of the puncture voltage and the flashover voltage. So here the puncture voltage is 125 and flashover voltage is 62.5. So answer will be 2. That is correct. So now we'll start with numerical problems. So this is the first question. Consider a three-phase 50 Hz 12 kV distribution system, and each of the conductor is suspended by a insulator string having a having two identical porcelain insulators, and the self capacitance of the insulator is 3.5 times the shunt capacitance between link and the ground. The voltage E1 is that we have to calculate. First of all, we have to make this. Let us draw the diagram first and using the information given in the question. So since there are two identical insulators, so there are two units, and here is the conductor. This is conductor, and then it is connected to the tower via two insulators. The two insulators are there, so there are two capacitances to represent these two insulators, and then in between there is one capacitance between the tower and the insulator string. So for n units in the insulator string, there will be n minus 1 capacitance is Cs, n minus 1 capacitances between the string and the ground. So it is the link capacitance. So it is a capacitance between, so there is only one link here, one link to connect the two units of the insulators. So the capacitance between this link and the ground, because tower is connected to the ground, it is grounded. So capacitance between this link and the ground is, it is Cs. And if this is C, the two capacitance representing two units of the insulators, and it is given that the insulator, the capacitance of the insulator is 3.5 times this capacitance between link and the ground. So as per the question, C is 3.5 times CS. Is this clear?
.89.
Sorry, can you repeat again? Oh, you are saying answer. You are saying 3.89. So
Yeah, yeah.
which one you have considered E1 and which one as E2? So if this is C, this is 3.5 C, and this is 3.5 C. So this one you have considered as E1 or E2? Which one you have considered E1?
First one that 3
First one
point.
is E1, and this one E2, right?
Yeah.
Okay. I think answer is uh, A. Means your answer is correct. One of the voltages is 3.89, but I think E2 is 3.89 and E1 is 3.03. Are you sure E1 is 3.89? Can you check?
Mm,
You can check it once again.
yeah. Okay.
So if we let us consider the current here is I2 and this current goes to here because it is ground here, I1 dash, and this is I1. So we can write a KCL at the node A. KCL at node A, and I is equals to Y into V, right? And Y is 1 by Z, or the admittance, which will be, so Z is 1 by J omega C. So Y is inverse of Z. Y is 1 by Z. Y becomes J omega C into voltage V. So now we have to write KCL at node A. It will be I2 plus I1 dash plus I1. So I2 is equals to I1 dash plus I1. So can you tell what will be I2 in terms of voltage and capacitances? So we can use this relation. We have to see which voltage is to be considered for I2. So this is E2, this is E1. So what will be I2? So across this capacitance through which the I2 current is flowing, voltage is E2, right? This voltage is E2. It will be J omega, and capacitance is 3.5 C. Voltage is E2, and this is equals to I1 dash. I1 dash is this current, and voltage here is this voltage, and this point are equipotential at same potential. Both are at ground. So voltage across this capacitance will be this E1. So voltage across these two capacitances is same, which is E1. It is, sorry, I made this is correct. So J omega C into E1, correct? And then current I1 will be J omega C, here is 3.5 capacitance, and voltage is again E1. Now we can just solve it. 3.5 E2 is equals to into 1.1 E1. So E2 comes out to be how much? 1.1 E1. Now it is already given that the voltage is 12 kilovolt, and this is line voltage. And we know that the sum of these two voltage is equals to E1 plus E2 is equals to which voltage? Line voltage or phase voltage? Which one? Phase voltage or line voltage? Anyone? This insulators are for each phase. So this voltage has to be phase voltage. Now you can substitute E2 as 1.1 E1 here and you can solve. I think I made a mistake here. This is 4.5 E1. Sorry. Yeah, so this will be 7 E2 is equals to 9 E1. So this you can substitute here. And you can find out E1 and E2 using this equation. So can you please calculate E1 and E2? Can anyone of you tell what is E1 and E2? Substitute E2 as 9 by 7 E1 here. So it will become E1 plus 9 by 7 E1 is equals to 12 by root 3. So E1 will be 12 by root 3 into 7 by 16. So what is the value? Can you calculate? Can anyone of you please calculate this value? Anyone? So are you able to understand? Is there any problem? You can ask if you are not able to understand anything. I can explain it again. If you calculate this, you will find out that even comes out to be 3.03 kV. Yes, so I have solved here. And this is even and E2 will be 1.1 times E2 will be 9 by 7 times even, and you can find E2 also 3.89 kV, and you can also find out the string efficiency. So can you tell what is string efficiency? It is a ratio of which two values? It is a ratio of voltage across the string divided by n, which is number of units in the string, into voltage of the lowest unit in the string, which is here this one. It's voltage E2. E2 comes out to be 3.89, number of units 2, efficiency comes out to be 89.05%. Is this fine? Any doubt in this question? You can ask if you have any doubt. Is this fine? Shall we move ahead? So you have to remember this voltage has to be phase voltage 12. Whenever, unless otherwise specified, always the voltage is line to line voltage, three phase line to line voltage. If it is phase voltage, it has to be mentioned. If it is not mentioned, then we have to take it as line voltage because we have insulators for each of the phases. We have to use the voltage E1 and E2 will sum up to be phase voltage. Okay. Okay, so next question. So the answer is for this question E1 is 3.03 kilovolt. Similarly, we have already calculated E2 also. E2 is 3.89 kV. That is the next same question. And efficiency also, we have calculated string efficiency. So what does string efficiency, what information string efficiency provides us? Uh, can you tell one thing? Why are we using this value as E2 3.89? Why not E1? That is 3.03 volts. This thing will come in next. In I think in the last question. The voltage which here. Why are we using this? Yes.
Because that one is the lowest
Lowest
part of
variation.
the.
Lowest, but that was I was saying. In one question which we will see, I think it's the last question. The lowest unit doesn't have the lowest or highest voltage. So in that case, will this formula be valid? Do we always have to consider the lowest unit's voltage? Or why are we choosing that lowest voltage, lowest unit voltage? That is the question. And that provides us a very important information. And that is why we are calculating this efficiency also. Why we are taking, if you take E1, E1 is 3.03 kV, E2 is 3.89 kV. We have to design the insulator with the all the insulator with the highest voltage. We cannot have insulator of different voltages. If we have it, because we want there is a standardization for everything. Because if we make insulator for different voltages, then for each transmission line it will be different, and we'll have to keep spare part for each transmission line. That is not a economical proposal. We always want a standard. So that is why we said that one unit is roughly 11 kV. So that's a standard that we have considered. We have to make all the units with the same voltage. So that has to be the highest voltage. Because if we make it with lowest voltage, then the insulator, which has a voltage higher than that, will have problem of this failure. So in here, in this example, the lowest unit has the highest voltage. But one example which we will see, although that is not a practical, not that practical, generally it will be highest at the lowest unit for the lowest unit. But if we see that example, then and if we implement it, then it is not necessary that the lowest unit will have the highest voltage. So whichever unit which has the highest voltage, that has to be taken for the efficiency because that is the highest voltage and all the insulators will be rated at that voltage. And because other insulators, although they are rated at 3.89, but their voltage across them is only 3.03. So that there is a wastage of around, let's we can say, zero point 0.8 kV insulation. We have an additional insulation of that zero point 0.8 kV. So we have to bear that additional cost, extra cost for that. So that is a loss in efficiency. So it gives us an indication of wastage of insulation. Is this clear? It will be more clear when I will show that example. It's a very interesting example because that will happen when we have that additional guard ring here, and that we use so that we what we can do, we want to equalize these voltages. Here only 2 units are there, but if we generally more units are there, and we want the voltage across them to be equal so that string efficiency is close to 1. And for that we use this extra arrangement of this guard ring, and which so it creates another capacitance, and this cap- capacitance will try to cancel this current I1 dash. So it will provide that current Ix, and because this current and this current cancels out, this effect of this capacitance is no more to be seen. As a result, the voltage across this unit also reduces, and it equalizes between these two insulators. So that example we will see at the end. The E2 also we have calculated, even comes out to be 3.03 and E2 is 3.89 kV. So this is the next question. This is also a very good question. Let us see how we can solve this. So in string insulator, it's a very simple question. If you see, so you can tell me how we can solve this. You can think about it. A string insulator has 3 units, and 40% of the total voltage. I think it is should be 50%. So 50% of the total voltage is the voltage across the bottommost unit, and we have to find out the string efficiency. So can you think how to solve this question? So let us make this structure first. Instead of two units which we had in the last question, in this question there are 3 units in the string insulators. These are the 3 units. This is a conductor, and then we have two capacitances for each link to ground capacitor. This is C and KC. K is between 0 and 1. Generally, it is between 0.1 and 0.2. Now, it is given that voltage across this. Let's say, let us call this voltage as E3. So this is E1, this is E2, and this is E3. So it is given that E3 voltage across E3 is 50% of the entire voltage for this phase. Only this information is given. We have only three units, and 50% of total voltages across the bottommost unit, and we have to find out the efficiency. So can you think how to solve this question? How to proceed? Any idea? You can guess. You can think little bit and tell. We'll solve it. So there's no harm in trying, because in exam also you'll have to think for certain questions. It's an easy question. You just think what all information are given and how we can use that information in the simplest way. Try to recall the formula for efficiency. So if you write KCL here, how many equations will you get? Can you tell me? How many equations do you have and how many variables are there? Can you tell? If you write KCL at, so we have here two nodes, right? Node A and node B. If you want to write KCL at these two nodes, node A and KCL at node B, how many equations do you have and how many variables are there in those equations? So in previous example also we wrote KVL to KCL equation for one node. In that example K was known, but here we don't know K. We don't, C will cancel out, so we don't know K, but we don't know even E2 also. So can you tell?
Sir, two equations and I think three variables.
What are the three variables? So one is E1, E2, and K. Do you have one more equation? We cannot solve two equations with three variables. We need one more equation. Do we have one more equation? So we have one equation relating E1, E2, E3. Right? We know that E1, E2, E3, if we take entire voltage as 1% because 100%, 100% because, and 50% is across E3 only. The rest 50% is, or we can directly say that E1 plus E2 is 50%. So we have now three variables and three equations. So we can solve, right? Is there any other way to solve this using the relationship that we know, using the definition of efficiency we know that we already seen in the last question? Can we use something from that? Can we use that definition to solve this question? We saw that efficiency is voltage across the string, right? So this is one way to solve this question. Method one, you can see. This is method one. You write the three equations, solve them, you will get answer. You will get the answer. Then another way, the same thing, because efficiency is derived using these thing only. Once you get all these value, you will put that in efficiency. But we directly know the information which is available to calculate efficiency. So this is n voltage across the string divided by n, where n is the number of units, which we know here it is given as 3 units, into it's multiplied by the voltage of the bottom most unit. And this also we know, right? So what is the voltage across string here? Can you tell? Just now we discussed it. What is the voltage across the entire string? As per the question. It is 1, right? Because it's given in percentage. 50% is, so we can consider that entire voltage is 100%. Number of units is 3, and voltage across the bottommost unit is also, it's given as 0.5. So how much is this? So can you tell how much is this? Well, what is the value of the efficiency? String efficiency. This is the method 2. Here we are directly using in the definition of efficiency, string efficiency. Here in this method 1, you will first calculate value of k, E1, E2, and then you will substitute again in this and find out efficiency. But here, because we already know this, all these values, we can directly use this definition. It will come out to be 2 by 3, 2.66, 66.6%. Yeah, the same thing written here also. So is this clear? This question? Any doubt in this question?
No, sir.
Yeah, so simple question, right? So same question you could do. Same question can be done in 2 ways, but this is more very easy way, very one-liner. So you have to think whenever you are solving question. So if we can solve that question in a shorter way, why to take a longer way? We can directly use. So we have to read the question very carefully. What are the information are given in the question, and can we utilize it in a very simpler way so that we can find out the answer. So for that we have to read it carefully and relate it with the knowledge, the concepts that we have studied, and then try to solve it. So the answer is 66.6. Now this is the next question. So question is the ratio of capacitance between pin and earth to self capacitance is 0.175 for a string insulator with 2 units. So it's a simple question with, so it's a simple structure. We have only 2 units, which makes our calculation also very easy. We have to write only one nodal equation, one equation, KCL equation. So we have 2 units of insulator. This is a conductor, and we have one pin to earth or link capacitor, and it is given that the ratio of this and this capacitor CS by this C is 0.175. So this is 0.175 C, and this is C. Then what else is given? That the maximum voltage across any unit should not exceed 11 kV. So we already know that the maximum voltage is on the bottommost unit, and this and its voltage, its maximum voltage that it can withstand is 11 kV. That is also given. Let us consider this voltage as E1 and this as E2. And it is given in the question that E2 is much 11 kV. Okay. Now we have to find out the maximum line voltage. So we have to read the question very carefully. This is line voltage, not phase voltage, that the insulation system can withstand. We have to find the line voltage. So how to solve this question? Is also similar to what we did, right? So you can consider a current of I2 here. So this is I1 dash and this is I1. So we have to write again a KCL equation at this node, at node A. This will be I2 is equals to I1 dash plus I1. So what is I1? What is I2? Can you write what is the value of I2 here? I2 is j omega C. This admittance of this capacitor and voltage across this is E2. J omega C E2. And I1 dash is current. So this capacitor and voltage across this capacitor is same as voltage across this capacitor, which is even. So J omega 0.175 C even plus same voltage across this also. So it is J omega C even. Here J omega C will cancel out and you will get E2 as 1.175 even. So now we have this relationship between E2 and E1 and we want to find out line voltage. So we have to find the entire voltage across this string. For that we have to add E1 and E2. We have to find out E1 also. So we have this equation E1 and E2 is equals to this will be the phase voltage. For that we need to find out E1 and E2. We are already given that E2 is 11 kV. This is equals to 11. So even we can find out. Even will be 11 divided by 1.175. So how much is this value? Can you calculate? Please calculate this value. How much is this? Anyone? So what is this value? Turns out to be 9.36 kV. Okay. So you can add even in E2. E1 is 11 and this is 9. 20.326. Which answer is correct? Can you tell which answer is correct here? We have found out even plus E2. What is the answer? A, B, C, or D? Now it's very easy. You can tell the answer. Anyone? Please. We have found out E1 plus E2. What will be the answer? E1 plus E2 is 20.326. What is the answer out of A, B, C, D? No one? Sangeeta, can you tell?
That option A.
Which one? A. Option A.
Yes, sir.
Are you sure? Is everyone with option A? How many of you are with option A? You can raise your hand also. Option A. Only one. What about others? What? Which option do you feel is correct? Okay. Sangeeta and Anshuman say option A is correct. Okay, so can you tell Anshuman this E1 plus E2 which we have calculated, is this phase voltage or line voltage? Satyendra says C. Why C? Because how can it be C? E1 plus E2 has to be either of the two values, either the phase voltage or line voltage. That we have to confirm. Is it phase voltage or line voltage? If it is line voltage, yes, that is correct, Satyendra. So E1 plus E2 is phase voltage, and in the question we have been asked to calculate the line voltage. Now, can you please tell which answer is correct? Are you still with option A? Anshuman and Sangeeta, do you want to change your answer? And Satyendra, you also. What do you feel now? A or B? C is already ruled out. D also cannot be the answer because either it is 20.32 or root 3 times. Because you already said that E1 plus E2 is the phase voltage. So what is the answer now? Please tell. Now it's very easy. Everything we have calculated. You can write in the chat box also. The answer is B. Yes, Roshan, correct. Answer is B. Thank you, Roshan. So E1 plus E2 is phase voltage and we want line voltage, so root 3 times 35.26. Next question. So, are you facing any problem, difficulty in understanding these things? You can ask any question if you have. So shall we continue with the next question? If there are no doubts. So this is a very easy topic. Insulator is a very easy topic, and you can easily score in this time. You can easily solve these questions. You just have to write KVL or sorry, KCL at each node and then solve the equations. To the last slide, okay. Which one's this one or this one? This slide, Roshan? See, I will also upload all these solutions which we are doing. I will upload this PPT so you can always, you will have these solutions with you. And after assignment deadline is over, the solution will also be uploaded on the portal. So both ways you can always have a look on the solutions. Okay, shall we move? Roshan, can we move further?
Yeah, sir.
Okay. So this is the next question. Each conductor of a three-phase overhead transmission line is suspended from a crossarm of a steel tower by a string of 4 suspension insulators. So here we have 4 insulators. So this is a standard practice whenever you are getting you get a question on insulator, just see the number of insulators and first of all draw this figure, uh, mark these voltages because we have to write KCL at each node. If you have a lot of you have done a lot of factors, then you may even directly write equations, but it's always a good practice to draw this and then write so that you can avoid any kind of mistakes. So these are the four insulators. I have drawn them. Let us mark the voltages. This is E4, this is E3, this is E2, and this is E1. And these are the current I4, I3 dash, I2 dash, I1 dash, I1, I2, and I3. So we have four suspension insulators. The voltage across the second unit is 12 volt and across the third unit is 16 volts. It is given that E2 is 12 kV and E3 is 16 kV. Now we have to calculate the ratio of capacitance between pin and earth. So which is this capacitor. Two self capacitance of each unit, which is this. So let us say that this is K times C, where K is less than 1. And this is C. All these capacitance, self capacitances are C. So we have to find out this value of K. So again we have to write the basic step is same for almost all the questions. We have to write KCL at different nodes. Let us say this is P node P, this is Q, and this is R. Since we already know these two E2 and E3, so we can write KVL at these two nodes. So KCL current law at these two nodes. Let us write KCL at node P. So it will be I2, which is I1 dash plus I1, and this will be j omega. Same thing again. C E2, which is now I1 dash and I1. The voltage across these two capacitors is same. It will be j omega Kc E1 plus j omega C E1. So E2 is, so this is standard for first node. This equation is always valid unless there is a capacitor for that guard ring. If it is not there, then this is valid always. E2 is K1 plus K plus 1 times E1. But in this equation, we only know E2. K we don't know, E1 also we don't know. So we cannot solve it. We need another equation. We need more equation. We have to write another KCL at this node Q, because we know E3. So here KCL will be I3 is equals to I2 dash plus I2. And again, I3 is this current. So this is the voltage here across this capacitor is E3. So j omega C E3 I2 dash. So now, till now, we were having only one link capacitor. Here we have second one. So the voltage across this capacitor will be how much? Can you tell? So this voltage, we want to know this voltage. And this voltage, these 2 points are same. This point and this point is same. We call this point A and point B. Point A and point B are same at same potential. Both are connected to the ground. So what is the voltage between this point A and Q? The voltage across this capacitor Kc. Can you tell what is the voltage? This voltage is this, right? Voltage. Can you please share this PDF? Yes, yes. The PDF will be available on the link. I will We'll share the link also in the chat box just after we have finished this discussion. Okay. So this voltage is E1 plus E2, right? Because this is the point B, which is same as point A. Both are connected to ground, and this is Q. And we want this voltage AQ or BQ, both are same, which is E1 plus E2. This voltage, E1 plus E2, the sum of E1 E2. Then I2, this is I2 dash. I2 will be voltage across this capacitor is E2. So it will be J omega C E2. So now you can write it as E3, which is equals to K E1 plus K plus 1 E2. So now we know the relationship between E1 and E2. So we can substitute this value here. Because we already know E2, so what we can do, we can substitute E1 as E2 by K1 plus E2 by K plus 1. So it will be K times E2 divided by K plus 1 plus K plus 1 E2. E3 will be multiply this K plus 1. E3 we know it is 16. This is K plus K square plus 2K plus 1. So K plus 1 whole square, because this will be multiplied here. Okay. Now we have to, now this equation has only one variable. Which is that variable? Can you please tell? In this equation, we are here. So can you tell which is the variable in this equation? Let's say this equation number 1. What is the variable? We already know E, E3 and E2. So E3 is 16 and E2 is 12, so we can divide it by 4. It will be K square plus 3K plus 1 times 3. 3K square plus 9K minus 4K plus 5K plus 3 minus 4. So this is the equation. Oh, answer C is correct. So you can solve this equation. You will get two values. One will be negative and one is positive. Because you can see discriminant d square minus 4ac here is positive. So that's why there will be two distinct roots. One is positive, one negative. And if you calculate these values are, k comes out to be minus 1.8 and 0.18. K cannot be negative. It is always between 0 and 1. So capacitance cannot be negative here. That's why K is 0.18. Okay. This is the answer. Now we have already calculated this K value. So what we can do, we know E2, right? E2 is 12 kV, which is also E2 is equals to 1 plus KE1, and K is 0.18, so it is 1.18 E1. So E1 you can calculate from here, 12 divided by 1.18. How much is this E1? E1? Can you tell? What is the value of E1? It will be, it is 10.5. 169 kV. Now you know E1, you know E2, you know E3. You can also calculate E4 now. So you can write equation. This is the same question. Here we have to find the line voltage. Again, line voltage we have to find. So for that we have to find out all the values. E1, E2, E3 and E4. So for calculating E4 we have to again write KCL at this node. KCL at node 4. Till now we have not. Let's say this is node S. Till now we have not done any question for this 4 unit insulator string. So let us write KCL equation for this node. It will be J omega C into E4, which is I4 is this current. So we want voltage across this capacitor, which is E4. Then I3 dash is this. We want voltage across this capacitor. Since this point is same as this point, so we can say the voltage across this capacitor is same as this voltage between this point B and point S. The voltage between B and S is sum of these three voltages, E1 plus E2 plus E3. Which is omega Kc into E1 plus E2 plus E3 plus I3. I3 is this current, okay, so voltage across this capacitor, which is this E3 only. So this is J omega C E3. We can cancel out the omega C. We will get E4 is equals to K E1 plus K E2 plus K plus 1 E3. Now we already know this value of K. We can substitute. We also know E1, E2, E3. We can find out E4 by substituting values of K, E1, E2 and E3. E1, E2, E3 and K. You can find out E4 also. So can you tell what is the value of E4? Substitute value of K here as 0.18, E1 as 10.169, E2 as 12 kV and E3 as 16 kV. So can you please tell what is the value of E4? Just type, calculate it. Can you please please calculate this value? How much are you getting? Anyone? Did you calculate? Yes, this is the next question, right? We have to find out answer for this. Answer for first one was 0.18. See. Next question was this calculate same part of this question. Another part was so calculate the line voltage in kV. So for that we have to find out the value of this E4. So did you calculate this value of E4? KE1 plus KE2 plus K plus 1 E3. How much are you getting? Anyone? Roshan, did you calculate? No. E1 was this, E2, E3. E2, E3 was already given. E1 we had calculated. E4 will be this. E4 comes out to be this 22.85. And because the answer what is required is we have to calculate this. What do we have to calculate? We have to calculate the line voltage. So E1 plus E2 plus E3 plus E4 is the phase voltage, which will be around 60.3. And line voltage will be root 3 times 105.69. Okay, so this question is also done. The answer is B here. So E1 plus E2 plus E3 plus E4 will be phase voltage, and multiply it by root 3, you will get the line voltage. We have all the four values. Now another part which we can solve here is string efficiency. So voltage across the string, and then number of units 4 here, and voltage of the bottommost. Not string, bottommost unit. The voltage across string is around 60.3. You can calculate. N is 4, and voltage V4 we calculated. V4 is 22.85. So this efficiency will be how much? Can you please calculate this value? Anyone? Did you calculate? Yes. Yes. Who has calculated? What's the efficiency? Please tell me. Efficiency comes out to be 91.4. Okay. Is this clear? Are there any doubts? Please. What, Janvi, what is 65.6? How did you get 65? What is 65.6? Can you please tell? How did you calculate 65.6? No, efficiency, how 65.6? Are you using, no, how did you calculate efficiency? You use these values, right? 60.34, 22.85. Have I made a mistake? Okay, I think I have made a mistake, right? Yeah, okay, correct. Good, very good. So you said 65, right? That is correct. Yeah, it's good. You should. That it's correct, right? I can make sometimes mistakes. So that's why I was asking you to calculate. So these are very simple calculations. Sometimes it happens. So it's good that you are calculating. What is 65.3 something, right? So this is correct. It will be around 60.3 divided by 91.4. So 65% efficiency. This is correct. Thank you. So please calculate for the next question also, right? Yeah, this is the next question. This is a very important question, and I was telling you that uh, value of voltage, which voltage should be taken for calculating efficiency. This we will see in this question. That we will see in this question. This is a very very peculiar question, and here you will find that voltage at the bottommost unit is not highest. It's a simple, the number of the lesser the number of insulator, better is for us, because calculation becomes easier. More the number of insulator we have to calculate, more and more equations we have to write. So here we have only two nodes. This is one node and second node. So we have to write only two equations. It's good for us. A, B. The number of equations increases, then it becomes difficult to calculate. This is I1, this is I1 dash, as this is I2, sorry, I3, this is I2, I2 dash, and this is, let's say, Ix. So let us read the question first. So these two voltages are even E2, and let us mark this voltage as E3. So now let us read the question. In a transmission line, each conductor is at 15 kV. Each conductor is at a 15 kV, which means, which is what is this voltage? Can you tell? Is this phase voltage? So you have three options: phase voltage, line voltage, then third is voltage across each unit. So which of these? Correct. Good. So this is phase voltage because it's for in transmission line each conductor. So each conductor means each phase it is at 15 kV and is supported by a string of three suspension insulator. We have already seen it in the picture. There are three insulators. Then so the air capacitance between each capacitor pin junction and tower is 1/5. So capacitance between this pin junction or this link, so it is pin called pin junction, or you can also call it as link. Okay, this capacitance between link and the ground is 1/5 of the capacitance of each insulator unit. That means it is 1/5 or 0.2 C. This is C, this is 1/5, so 0.2 C. So this is same as previous questions. The additional part here is this one. A guard ring effectively only, so this also first thing is guard ring. So these are the keywords which you have to see while reading the question. Each conductor, then three insulators, then 1/5, then guard ring, effective only over one line. This is also very important. Effective over only one line, and in one line and insulator unit is wasted. Effective over only over the line and insulator. Sorry. Effective over only the line and insulator. So it is only up to this for this last insulator. So it is not extending up to here. So this also we have to read carefully. In some question you may find it this guarding to be extended up to this point. So then there will be one more capacitance. But here we have only one capacitance, so we have to, so it will make our calculation even easier. We will solve that question also with this one more capacitor. What will happen? We'll see. So it is fitted only for this insulator such that voltage on the nearest unit to the line is zero point 0.8 times the voltage on the second unit. This is also very important. So these are the keywords. So what it says, E3, which is the voltage on the nearest unit to the line or the bottommost unit, E3 is zero point 0.8 times the voltage on the second unit, which is E2. So this information is given. Now using these informations, we have to solve this question. Let me remove this part. So now we have E3 as zero point 0.8 E2. This information we know. And as we have already seen, now we can write two equations. One is this, which is very simple, same as the previous questions. Sir, please explain garden part of the question. Okay, okay. So here what is happening up to this point, let me remove this entirely. Once again, I will explain this part. So first of all, why are we using this guard ring? So what is happening, we saw right in the previous questions also when there were three insulators or even two insulators, whatever number of insulators are there, without guard ring. So we have only this arrangement without guard ring. Right? So we have this N, let's say this is the nth self capacitance and this is N minus 1 link capacitor. So for N self capacitance, there are N minus 1 link capacitors because there are only N minus 1 link. So for this arrangement, the voltage at the bottommost unit, this Vn, will be greater than all the previous voltages, N minus 1, and it will be greater than N minus 2 and so on up to Vn. So this will be the basic relationship for this kind of arrangement. And we have seen even in the previous question we saw with four suspension insulators, the efficiency came out to be 65%, which is very less. It's poor efficiency. And this is happening because voltage across these insulators is not proportionate or not equivalent, not similar. It is different. The voltage here is less, then it increases, and all this is happening because of these capacitances, stray capacitances. It is because of these stray capacitances. If we remove these capacitances, and all these capacitances are identical, sorry, all these capacitances are identical, then what will be the voltage? Voltage across these capacitor will be same. They are connected in series, they will share equal voltage. So let's say the phase voltage is Vp, then this voltage across this capacitor will be Vp by N, Vp by N, Vp by N. So let's say if this is 30 kV, then voltage across each capacitor will be 10 kV, 10 kV each. If there are no stray capacitances. But when we have these stray capacitances, then this voltage distribution will change. Instead of 10, 10, 10, it will be something else. Let's say 7.5, some 9.5, and the remaining across this capacitor. This is just an example. You can values can be different also. So this it is happening because of these stray capacitances, and because of this efficiency is reducing, because efficiency is this phase voltage divided by number of units into voltage at the bottommost unit, and this is maximum, greatest among all the other voltages. So this dictates the efficiency, and this reduces the efficiency, but we want the efficiency to be close to 1. So for that we are making one arrangement which is called this guard ring. What we do, we want to neglect, so we want to uh, remove the effect of these stray capacitances. These capacitances are drawing some current. We always show this that like this, I2 current, I1 dash is going here, I1 is going here. So if this I1 dash somehow will make it zero, then entire I2 current will go to this same I1, I2 will become same, and the voltage will also be same. So what we do, we make another arrangement such that there is a capacitance between this link and this guard ring. We want to remove the effect of these stray capacitances. So we connect this guard ring, or it's a metal conductor. Its shape is such that these capacitances Cx, Cx dash somehow they mm, cancel the effect of these stray capacitances. So this I2 dash and this is Ix2, Ix1. So we want ideally I1 dash to be equal to Ix dash, Ix1, Ix1, and I2 dash to be equal to Ix2. If we ensure this, then this becomes, this effect of this current is gone, because whatever current is going here, because will be supplied by this, so that these two currents, whatever I2 is there, I1 will become same, because no current is being drawn here, it is being all supplied by this Ix. So in resultant we will see I2 plus Ix1 is equals to I1 dash plus I1, and both these current are equal, cancels out, so I2 becomes I1. So this we want to do, and for this purpose we are using the guard ring. So is this clear now, Roshan, and everybody else also? Is this clear? Why are we using guard ring? Okay. So this is the question. It's a very important concept. Very, and we will see. We'll play with this example. It's a very good example. So many things we can see from this one example. So we'll see three parts of this example. Now, what we have to do, we have to write two KCL equations. That for so KCL equation at node A first, node capital A. So this is I2 is I1 dash plus I1. This we have solved many times, and because there is no other capacitor here, this guard ring is not there, so it will come out to be E2 will be K plus 1 E1. Same as previous examples. If this capacitance is there, then it will be different. So this is for the first node A. Now we have to write KCL for node B. Node B. This is the node B. So for now, this will change because of this additional capacitance, which want to cancel the effect of this stray capacitance. Now this will become E I3 plus Ix is equals to I2 dash plus I2. Okay. So I3 will be same. This is I3, so you have to voltage across this capacitor is E3. So it will be j omega c E3 plus Ix. Ix is now voltage across, Ix is current through this capacitor, and these 2 points are same. The voltage across this Cx capacitor is same as voltage across this capacitor, bottommost unit. So this is also IWCX E3, which is I2 dash. Now I2 dash is this current, and we want voltage across these 2 points, point A and capital B, which is same as point B and capital B, which is E1 plus E2. So this is J omega point 2 C into E1 plus E2 plus I2. I2 is this. So we want only this voltage. So J omega C E2. Now we can solve this. So here now J omega will cancel out, but C will not cancel out because here we have C and here it is Cx. So it is C plus Cx into E3. C plus Cx into E3, and which is equals to point 2 CE1 plus 1.2 CE2. Now here K is known, right? K is 0.2. So E2 is 1.2 times E1, right? We can substitute this here, E2. Sorry, yeah, this is not here. This is J omega C E2. We can substitute this E2, replace this E2 by E1. So this 0.2 C E1 plus 1.44 E1 into C, which is 1.64 C E1. Okay. Or no, we have to change it because E1 is not known. We know the relationship given is this. E3 is zero point 0.8 times E2. So we have to substitute not for E2 but for E1. From here you can write E1 is equals to E2 divided by 1.2. So let us change this. So it will be 0.2 C. E1 will be E2 by 1.2 plus 1.2 C E2. Okay. Now can you tell what is this value? Please calculate. So you can see C by Cx. E3 you know, E2 relation between E3 and E2 you know. So you can substitute that and you can find out C plus Cx is equals to some K dash into C. This will be C plus Cx. And from here you can find out relation between C and Cx. So did you calculate? Any one of you? To try to solve this. One point 33 CE2. Okay, just a minute. 1. 3 Ce2, which is equals to C plus Cx into E3. Now we know that E3 is 0.8 E2. So this 1.33 C into C plus Cx into E3, which is 0.8 E2. So this is into 0.8. 1.36. Okay, no problem. So now, can you calculate relationship between C and Cx from here? It is 1.36 divided by 0.8. 1.7 C is equals to C plus Cx. So Cx comes out to be how much? It's very easy, right? How much? So this is, what is Cx now? Which option is correct? Yes, correct. 0.7 is correct. So it is done. It is solved. No? This is 1.7, so Cx comes out to be 0.7. So this is correct. So this is part A of this question. Now we will see. We have calculated Cx. We want to calculate efficiency. Let us calculate efficiency. So for efficiency, we need E1, E2, E3. So let us find out E1 here. E1, we know that E2 is 1.2 times E1. E3 is 0.8 times E2. So this is how much? 0.8 into 1.2 E1, which is 0.96 E1. So voltage across the string will be E1 plus E2 plus E3, which is 1 plus 1.2 plus 0.96 E1. So what is this value? 1.1. Is this correct? Yes. Okay. Now, how can we calculate E1, E2, E3? We know relationship between E1, E2, E3. How to calculate E1, E2, E3? Can we calculate the values of E1, E2, E3 using information given in the question? We have one more information. We know the voltage across the line conductor is, phase voltage is 15 kV. So E1 plus E2 plus E3 is 15. So this is 3.16. E1 is 15. E1 is, how much is this? Please calculate. 15 divided by 3.16. How much is this? So how much is even? And E2 is 1.2 times E1. And E3 is zero point 0.8 times E2 or 0.96 times E1. Now you can clearly see here. In the previous questions that we did without this guard wire or guard ring, the E3 was the highest voltage, right? The bottommost unit was having the highest voltage. But here E3 is 0.96 times E1. That means it is lesser than E1. It is least here. In this example, E3 is least. Yes, so how are we going to calculate efficiency here now? Highest, which value is, which voltage is highest in among these three, E1, E2, E3? Can you tell? E1, E2 or E3? Which one is highest? Please answer. E1, E2 or E3? Which one? You can write 1, 2 or 3. Yes, E2 is highest. So efficiency we have to calculate using the highest voltage. So here it will be 15 divided by 3 into 5.7. Please calculate what is this value? What is this value? How much is this efficiency? Yes, 87%. Now this is efficiency considering this one, the guard ring which is extending only for the bottommost insulator. Now we will see what is the efficiency. Answer this we have already calculated, zero point 0.7. Sorry. Yeah, so that was the efficiency 87% with guard wire, covering only one insulator. Now we calculate the efficiency without guard wire. What is the efficiency without guard wire? So this is same as previous, the way which we have done for other examples also. So you can find out E1, E2, E3 will come out to be this. Here you can easily see E1 is 3.96, E2 is 1.2 times, and E3 is highest. So it is 1.64 times E1. So E3 comes out to be 6.40 without guard wire. So efficiency here goes to 78%. And efficiency with guard wire was, guard wire, let's say only one, extending only one insulator, that is around 87%. Now what we can do, we can again calculate this efficiency. Let us do it again here. Just remove this. Let me add one more page. Let's do it here. So now let us consider we have extended this guard wire up to the second insulator. Let us see what happens to the voltage distribution as well as the efficiency. So now this is also Cx. Okay. Let us consider the Cx is same as 0.70. Okay. So in that question, because we wanted this voltage to be 0.80 times that, Cx came out to be 0.7. We don't know what will happen to this voltage with this value. Let us see. I have also not calculated this. Let us try out. what happens to the voltage distribution. Certainly the efficiency should improve a bit. So now here for both the nodes we have to write the equation. So for node 1 it will be I2 plus Ix, which is this, let us call it Ix1. This, then it is I1 dash plus I1. So I2 dash, let us mark I2, I1 dash, I1, I3, I2 dash, and Ix2. Okay. So I2 dash here will be j omega c E2 plus, and Ix1 will be across this capacitor. This point is same as this. So what is the voltage? It is how much? J omega Cx into E2 plus E3, because this point and this point is same. So we want this voltage, and this is equals to I1 dash. I1 dash is this voltage. So these two voltages are same. J omega 0.2 C I1 dash plus j omega C I1. So this will be Cx, we already know this is point, let us 0.7 C. So j omega C will cancel out, E2, or you can say 1.7 E2 plus 0.7 E3 is equals to, oh, I made a mistake, sorry. This is E1, E1. This is 1.2 times of E1. So this is one equation relating E1, E2 and E3. Similarly, we have to write one more equation here. So this will be I3 plus Ix2 is equals to I2 dash plus I2, which is j omega c E3 plus Ix2. How much is Ix2? It is j omega 0.7 C E3, which is equals to I2 dash here is j omega 0.2 C into E1 plus E2 plus j omega c E2. J omega c will cancel out. Again we get 1.73 E3 is equals 1.7 E3 is equals to 0.2 E1 plus 1.2 E2. Now these are the two equations. So can you solve these two equations when one more equation is E1 plus E2 plus E3 is equals to 15? Can you solve this equation and find out E1, E2, E3? Do you have calculator? Or you can substitute for one of these E1 from here in this equation and this equation. Then you will get two equations. One equation is this, second is 1.2 E1 plus 1.7 E2 plus 0.7 E3 is equals to minus 1.2 E, then minus 0.2 E1 plus 1.2 E2 plus 1.7 E3 is equals to 0. So this is a system of linear equation. We have three equations. So you can solve them. Okay, I'm solving it using calculator. If someone of you have solved it, then you can tell me. Even in this case, E3 is coming out to be negative. So that means this value which we have taken 0.7 is not a good value. We have to change it. But clearly, one thing we can see, voltage across E3 is negative. The zero point 0.7 value is very high value. It is showing that this 0.7 value is very high. So one thing which we can do is we can calculate this value of Cx, which is zero point 0.7, by making this 0.8 as only 1. We can E3 is equals to E2. If we make this, then we find out what is Cx. It will be certainly less than 0.7 Cx. And then we can calculate. So is this clear? I was trying to tell you so how we can solve this. Maybe I will find out this value with 1 and put it in the slide. So is this fine? Because I didn't solve this, I was just trying to solve it, but here I didn't realize that 7.7 is a very high value and this will come out to be negative. And certainly we have to make it, by making it 1, certainly the value will be much less than 0.7. So we can actually, I will solve that and share it with you. So if you have any question, you can ask. We have solved all the examples for today. I hope this session was beneficial for you. And the way which we proceeded is that we started with a very brief overview of week 1 and then we solved the questions. If you want me to directly start with questions, I can do that also. So you can please, you can always provide your suggestions. So the way which we follow today, is it fine, or shall I directly start with the questions? Please, you can comment on this. How would you want the session to be? Okay, so from next time onwards, we'll try to do the same thing. We will quickly go through the overview of that week, and then we will take numerical questions. So we can also revise certain concepts. Okay, are there any other doubts? If not, then we can end this session. Oh, link of the slide. Yeah, sure. Let me. Yes, you will get the recording of the session. In that portal, you will find the link also, link for the Google Meet as well as the presentation which I have used. From there, you can download. On the portal, you on the left hand side where you find assignment, right? Below week, you will also find one link for problem solving session. In that, you will find a link for Google Sheet. There you will find all the links for the PPTs as well as the YouTube. Right now, I have not uploaded it on Google Drive. After this session is over, uh, I will create a Google Drive and share. Maybe before the next session, you will also get the portal will be updated. So is okay. Okay. So thank you for joining. I think soon the portal will be updated and you'll be able to see the link for all the recordings as well as the PPT. So thank you very much for joining. We'll meet on the next Saturday for discussing the week 2 problems. Thank you.